Good evening, 8-bit physics students. Here's Mr. Kirsten. We're going to be lecturing today about Newton's universal law of gravitation and the rest of chapter 5. So, as we know, Newton's universal law of gravitation states that any two objects in the universe that have mass are attracted to each other, right? And the force of that attraction is equal to a constant, big G. That's actually what physicists call it, big G, times the mass of object 1 times the mass of object 2 divided by the square of the distance between them, between the centers of mass of each object. And of course, it was Isaac Newton who first came up with this. Rumor has it he was sitting out in an apple orchard thinking about this when an apple fell and hit his head, and that's when it came to him, or so the story goes. Big G can actually be measured in the laboratory. Notice it's very small, of the about 10 to the minus 12th power. So that's very small. So in order for this force to be measured, you either have to have really big masses or really sensitive equipment. And this constant was first measured in the 1800s by a British physicist named Henry Cavendish. And anyway, this won't be on a quiz or a test or anything, but what he did was he had two objects that were attracted to each other, and what that did is it twisted this, and the very slight twist of bringing this object next to this object, you couldn't notice the twist of this object unless you shined a laser light at it. Well, it wasn't a laser, it was the 1800s, but a light source, narrow beam, and when it moved just a little bit, it would move over here on the scale. And anyway, once big G was experimentally determined accurately, we could weigh the Earth. So Cavendish was the first person to weigh the Earth. How did he do this? Well, he knew that the weight of an object should be equal to mg, little g this is, right? This is 9.8. And the radius of the Earth was known, so basically if everything in this equation was known except the mass of the Earth, you could solve for the mass of the Earth. So he did that and figured out that the Earth's mass is 5.98 times 10 to the 24th kilograms. So if you see that number in the front of your book, it's not because we've placed the Earth on a big scale, but we've actually measured the mass indirectly by knowing the universal gravitational constant, the acceleration due to gravity, and the radius of the Earth. So Cavendish, using his value for big G and Newton's universal law of gravitation, weighed the Earth. So we've talked about this before. The acceleration due to gravity varies some based upon local geology, the Earth's shapes, elevation, that type of thing. I do want to talk about weightlessness a little bit. Some people say, oh, like astronauts up in the space shuttle, they're weightless. And the answer to that is not really. The acceleration due to gravity is actually about 90% in orbit of what it is on the Earth, but they appear weightless because they're in constant free fall. If you're in a circular orbit, you're constantly falling around the Earth. So that's why you appear or feel weightless. You know, the idea is if you're in an elevator and someone cuts the cables and the elevator's falling at the same rate you are falling, you don't feel any forces between you and the elevator, so you feel weightless. Weightlessness isn't necessarily the lack of gravity, it's the lack of a normal force. So anyway, when you're in an elevator that's free falling, hopefully you're never in an elevator that's free falling, but if you are, it's not that gravity's not pulling down on you, it's that the elevator is not pushing back up on you. So weightlessness is more of a lack of normal force than it is lack of anything else. So when you're flying through the air, it's not the and feel weightless. We call that apparent weightlessness. Gravitational force of the Earth is still there. Um, it's just there's no normal force. Okay, so let's talk about Kepler's laws a little bit. So a guy by the name of Keppler um, came around and said, you know what? The planets don't actually orbit in perfect circles. They orbit in ellipses. What's an ellipse? It's the set of points that the sum of their distances, so if this is a planet, the sum of the distance from two foci is a constant. You could, if you put two tacks here and put a string of fixed length here, you can draw, that's how you draw an ellipse. So the sun's at one ellipse and the planets actually orbit in ellipses instead of circles. Now they're really close to circles, but they're actually ellipses. So anyway, Kepler's laws can be derived from Newton's laws, but Kepler's laws are a little more descriptive. And one of Kepler's laws says, Kepler's second law says that when a planet is close to the sun, it's moving very quickly, and when it's far away from the sun, it's moving very slowly. However, if you have an imaginary line between the sun and the planet, that line sweeps out equal areas in equal amounts of times. So, for instance, if this was, 1 Earth year, this area here would be equal to, this would also be 1 Earth year, and this area would be equal to this area. So that's one of Kepler's law. Planets sweep out equal area in equal times. So, okay. Let's see here. So, let's talk a little bit about fundamental forces. So there are only 4 types of forces in nature. Every other force is just a combination of these. They are 4 fundamental forces are gravity, electromagnetism, the weak nuclear force, which occurs inside the nucleus of an atom and is responsible for some type of radioactive decay, and the strong nuclear force, which binds protons and neutrons together in the nucleus. Anyway, that won't be on the AP test. It's just kind of interesting stuff. Okay, so there's a chapter summary here. We talked about circular motion and centripetal acceleration and centripetal force. And of course, this is a biggie, Newton's universal law of gravitation. All right. Okay, nice work, physics students. We'll do some example problems next. And of course, we didn't forget your reward for listening to Mr. Kirsten's lecture. A fun old Mr. Kirsten artifact. This is my 1991 marching band trophy. There you go. Fun stuff. All right, good job, physicists.